with those that don't do it. And that's a bad experimental design. It's bad because those that don't do it will be a different profile of people to those that do it. And you shouldn't do it that way. What you should do is you should randomly allocate people to the two groups. It makes it much harder because people often don't want to go into a study when they know there's a 50% chance they'll get a placebo treatment. But you need to do that, and you need to design your placebo treatment to mimic the time, attention and high-tech nature and convincing explanation of the real intervention. So especially if you're researching something like a vision therapy, you need to come up with a dummy vision therapy. And that's what we did in a study of nystagmus, for example. The subjects, we said, must be masked. The experimenter also should be masked for the reasons that we spoke about before. And you can use a statistical method to work out how many subjects you ought to be researching. So one of my doctorate students who, you might know, he comes to Israel quite often, he works with Simon Barnard, Alex Levitt. He's doing a research study with me comparing for keratoconus scleral contact lenses with gas-permeable contact lenses. And the subjects know which they're getting, but because we can't avoid that, you know, sclerals are different to gas-permeable, but we're telling them that we're comparing two new types of lenses. So they both have a belief that what they're getting should be helpful. And the person taking the measurements is not Alex. Alex Levitt is fitting them with the lenses, and he's checking they fit healthily, but when they come in and they have their acuity measured, that's done by a different person who doesn't know what sort of lens they're wearing when he tests their acuity. And in that study, we did a power calculation to ensure that we have the appropriate number. And this importance of doing a randomized controlled trial is never more important than when you are doing something that will generate a powerful placebo effect. And what will generate a powerful placebo effect is giving people time and attention. In other words, giving them vision therapy. So here's a real example that I'll give you in a moment. And the reason that placebo-controlled trials are so important in vision therapy is because the time and attention, and also many conditions, improve over time. So if you give everyone poor convergence exercises, many of them will just get better over time. Many variables improve with the practice of being measured, so they come into your office after vision therapy every week and you measure their convergence. Well, guess what? If you'd measured their convergence every week, they probably would have got a bit better even if you hadn't treated them. So that's why you need a randomized controlled trial. Don't be fooled by objective-looking data. This was a study on convergence where the people measured items to record convergence. And they said, look, we've not got a placebo-controlled trial, but that's okay because we had an objective measure. What does this really tell you? This tells you their convergence, but you could have seen that looking at their eyes. It's just a gadget to try and look impressive to patients. I don't think it's very useful. It doesn't make the research any more valid to do that, not much more valid. And with vision therapy, it's very easy for us to convince ourselves that a treatment works. People sometimes say, well, yeah, but the vision therapy I'm doing, I know it works. People get better. And even if that's just a placebo, surely it's a good thing to make people better. Well, yes, it is. But the problem with placebo treatments is they waste resources and time. They slow down the development of real treatments because we're all giving people placebo treatments, we're not developing proper treatments instead. And people sometimes say, well, look, I think my vision therapy works. If you don't, and there's no research, I think it works. You don't believe me, you do the research. But if you think about that, that just isn't a tenable viewpoint. We can't say, I believe in something, there's not good evidence. If you don't believe me, you do the research. The onus to prove that something works lies with those that believe that it works. You can't expect someone else to solve your problems. Another very important factor that I've read about a lot recently, and I'm becoming obsessed with, because I just don't think we appreciate this in optometry enough, and it's a fascinating thing that is just common sense. It's an effect called regression to the mean. How many of you have come across this phrase, regression to the mean? Okay, you see, we don't know about it, and it really should be known about. What this is all about is that if a variable is extreme the first time you measure it, and you don't give people any treatment, you just measure it again, the second time you measure it, it will be closer to average, on average. And if the first time you measured it, if it was extreme on the second measurement, and you look back at the first measurement, on the first measurement it will be closer to average. Now, as always, it's hard to get your head around until you think about an example. Let's say that you guys come into Hadassah and you have a test on something you've learned. And you then come in 2 days later, unwillingly I would guess, and you have another test on something that you've learned. So we've got 2 scores for you on 2 tests that have been matched, identical tests. The worst performers on the first day, even if you don't do anything between the 2 days, those who perform worse on the first day will tend to have higher scores on the second day. And those that are best performers on the first day will tend to do worse on the second day. And this has been proven time and again. Why does it happen? It happens because scores are determined by 2 things. Firstly, by what you know, that's why you have tests. But secondly, just by random events. By whether you're having a good day or a bad day, how well you concentrate, how well you understand the tests, and so on and so on. Now, if it was completely random, then those who did worse on the first day would, because it's random, those who did worse than average on the first day, if you were just guessing, and here was a multiple choice question, and you had to guess, and a 50-50 chance, so you'd expect you to get 50%. And the ones that did badly on the first day, because you are just guessing, you'd by chance do better on the second day. And those that did better on the second day would do worse, would be more average on the first. Because it's completely
if it
random.
is not guessing, if it's only guessing, to be the same on the first time and the second day.
Yeah, if there was no chance element in it, if it was purely measuring what you know, then you would be consistent on each occasion. But because it's going to be a bit of each, isn't it? It's going to be partly what you know and partly chance. So because it's partly chance, there's a regression to the mean. It doesn't say that everyone goes to the mean. It just means that if you have an odd set of readings, you're less likely to be odd the next time you test.
People who do the psychometric test, on the first time, they don't do so good. And when they do it more and more, they do it better.
That's
so
practice.
It's not
no,
right.
That's a different effect. That's a different effect. That's practice. What I'm saying is, if you don't have any practice going on, this would be what you would find. And if you did have practice going on, this regression to the mean effect will be overlaid on the practice that you have. What does it mean for us as optometrists? Because this is widely known, and if you think about this, it takes you a while to get your head around it, but it makes perfect sense. Because when we measure something, there will be a random element. Therefore, there will be an element, a partial effect, whereby it regresses back towards the mean. So if we're an optometrist, and we measure the person's near pointer convergence, everyone has an eye exam. Those are the near pointer convergence that's bad. We treat them all. When they come back, on average, they will do better the second time we measure them, even if our treatment isn't working. Now, I know what you're going to say. They'll do better, hopefully, because the treatment is working, or because they're practiced at the convergence test at the very least. But what this effect means is that the regression to the mean could explain our results. Doesn't mean it is explaining an improvement, but we need to control for this. And if you take the test of visual perceptual skills, we're going to talk about tomorrow morning, and you pick dyslexics who on one occasion when you test them, they do badly on this test, and you give them vision therapy, and they come back, you would expect them to do better even if your vision therapy hasn't worked. Now, hopefully they'll do better because of a regression to the mean, as well as because the vision therapy is working. But you shouldn't assume that's the case. Yeah.
But what why I don't understand why if they did worse, so now they'll do better. If they do better, that will be worse. It's supposed to be equally, randomly.
Yeah, it's because if you take people that do better than average, some of those people, well, let's take people who do worse than average on the first time you test them. Some of those people will be worse than average because they do have worse performance. And if you measure them again, it will be bad again. But some of those people who had worse performance on the one time you test them, it was just a bad day. They just are unlucky, or they didn't understand your instructions, they didn't understand the test. So if you look at 100 people who do badly when you measure their convergence, in that 100 people, there'll be some people who did badly because they've got really bad convergence, but there'll be some people who did badly for a random reason that's not to do with their convergence. So on average, if you measure them again, they would do better because the chances of them having a bad day on 2 occasions is very low. Now, I'm not saying that this means that vision therapy doesn't work, because I believe vision therapy does work. I'm not saying that it means we shouldn't treat convergence, because I believe we should treat bad convergence, but it's an effect that will account for some patients. So we need to deal with this in an intelligent way. Now, one way you can deal with it is you can measure them twice. And there's a famous paper on the prevalence of binocular vision problems that I read, and what the researcher did in this paper was he said, I will not classify anyone as having a binocular vision problem unless I get the same result when I test them twice. I didn't understand why until I read about this regression to the mean, and that's why he did it, and it's a really good research design. Another way that we can get around this,
if someone has a good convergence, you do one day, 5 centimeters good.
Yeah.
The next day, also 5. The next day, also 4, and also 5, and also 6.
Yeah.
It won't go worse, because the convergence is still here. So it doesn't matter if it's a good day or a bad day.
If it's good, it's good. But if it's a bad day, it might be bad for a genuine reason, or it might be bad for a spurious reason.
So it's right only for the bad convergence.
It's a good point. It's a good point. You could argue that, I guess. You could argue that with convergence. Yeah.
Because it's not possible that somebody will do 5 centimeters good one day, and after the conversion will go away, and he will do 20.
Yeah, I take your point. What I would say about this is the way we can get around this is the same way we can get around that problem that I talked about before of doing lots of tests and doing too many tests until somebody fails one of them. If you combine your test results in an intelligent way. So let's say you measure the near point of convergence and it's bad, you measure the positive fusional reserve and it's bad, but the divergent fusional reserve is good, and the amplitude of accommodation is good. Well, you're starting to get a picture then, aren't you? Your test results combine to point to a convergence insufficiency. And if you combine your test results, then you can overcome this to some degree. But you need to bear this in mind, and if you just take one test abnormality as being an indication for treatment, then this will mean that you get it wrong sometimes.
But usually when someone comes to an evaluation, you check a lot of things, and they combine to a big picture. Sometimes you can find one specific examination that didn't come well, but you can see that overall this person is doing well, so you won't send them to vision.
What you should look for, exactly. And what you're looking for in that is a person who's performing well in some tests and badly in others, so you know they're not just having a bad day. And that's really what I'm saying, is you need to take a holistic view and look at all of your test results together. Here's an example that we did. So when I took over the Institute of Optometry, the person before me had a vision therapy for nystagmus, and it was called IPS, intermittent photic stimulation. People looked at a flashing light box with special targets on it, and this person, this practitioner, believed this improved their nystagmus. And he looked at a case series. So he'd got people with nystagmus.
Hi there, Bruce.
I've got a new iPhone, I can't remember how to turn it off. Turn it off, great. He got people with nystagmus and he measured their acuity, and he started his treatment. He measured their acuity each week with the treatment, and he found their acuity got better. So he said this works. So when I took over, I said, okay, I want to do a research study. Now, again, I'm deliberately showing you bad science to make a point. So this is their research study. This is their visual acuity, logMAR visual acuity. So lower values are better. And these are people with nystagmus before they had the vision therapy and after they had the vision therapy. So lower is better, their acuities got better. And if you compare their visual acuity before to after, and you do a paired t-test, it's statistically significant, less than 0.05, so it looked like it worked. Except for, this would be bad science. Because the way I've shown this, we had one reading before, one reading after. Because of the effect I just showed you, regression to the mean, this could confound this measurement. Also, there's bad science here. The graph doesn't go down to 0. There's no error bars. And we have not had a control treatment. What we should have done, instead of just comparing the treatment before and after, is we should have had a control group having a placebo treatment. And that's actually what we did. So I've extracted some of the data here to make a point. Let me now show you what we actually did. What we did was we got patients with nystagmus. We made sure they had the right sort of nystagmus, so we randomly allocated them. We got people with nystagmus who had the right sort of nystagmus, their acuity was in the right range, and they were the right age, and so on and so on. And we got a group of these people, and we randomly allocated them to one of two treatments. Now, they didn't know which was which. The person taking the acuity measurements didn't know which was which. And half of them got the real treatment, the IPS treatment, and half of them got a placebo treatment. Now, the placebo vision therapy gave them as much time, as much attention, and we had a pretend explanation for how it was meant to be wonderfully effective. So we made up a lie about it. And the other thing that we did, because you know with nystagmus that when you measure people's acuity, with practice it gets better. They get more relaxed at having their acuity measured, they get less stressed, and it gets better. So we actually got them in for 3 weeks to measure their acuity each week before we started the treatment. So this is our group that got the real treatment, and you can see their acuity gets a bit better. Then when they have the treatment, after the treatment, it does get a lot better. Now this difference from here to here, this is a wider scale. That difference from there to there is what I just showed you from here. So this is exaggerating it because of the scale, but it's exactly the same effect, from about 0.36 to about 0.4. That's what we get here, from about 0.36 to about 0.4. So how about the control group? The control group, we did the same thing. We measured their acuity every week. Then they had their dummy treatment for 6 weeks. Then we measured their acuity at the end. Here's the control group. The dummy vision therapy, just as effective as the real one. So if we hadn't done a double-blind, randomized, placebo-controlled trial, I would be up here saying to you vision therapy for nystagmus works. Because we did a double-blind, randomized, placebo-controlled trial, the two groups were no different. The group that had the dummy treatment improved just as much as those that had the real treatment. So because we did a randomized controlled trial, we were able to say this vision therapy doesn't work for nystagmus. And without influencing you on whether you want me to talk about nystagmus on the last day, treatments don't tend to work for nystagmus. They're born with it and they die with it, by and large. So this was the first study I did that really made me aware of how prone to bias we all are, because I believe this worked. I believe this treatment worked. I'd seen people in the clinic seeming to get better acuity after the treatment than before, but this study showed that it was no better than a placebo. Now, I'm a passionate believer in the evidence-based movement, but you can go too far. This was a great paper. You know, in the UK we have April Fool's Day and people publish things that are a joke. And this was a paper that was published saying that they'd done a systematic review. Remember I said systematic reviews are the highest form of evidence. They did a systematic review of randomized controlled trials, there weren't any, to show whether parachutes are an effective intervention to prevent death if you jump out of an aeroplane. They said there are no rigorous randomized controlled trials to show that parachutes prevent death if you jump out of an aeroplane. Therefore, a parachute is not an evidence-based intervention, so we shouldn't be using them. I'd never jump out of an aeroplane without a parachute. So the joke here is that you can take things a bit too far. This was our worst newspaper in the UK is a newspaper called The Sun, and there was a headline in the Sun newspaper that said, "The Navy's painted submarines blue after extensive trials and lab tests." Well, duh, the sea's blue, so a blue submarine, why would you need to do extensive tests to work out that that's going to be a useful camouflage? So we need to have a bit of common sense. The designer of the randomized controlled trial is a person called Hill. He published in 1966 that the randomized controlled trials are very good, but don't believe it's the only way to get a result that means something. He said there's other forms of evidence other than randomized controlled trials that we should look for. And for example, single dissociation, I'm going to talk tomorrow morning about some eye exercises that we developed. And when we developed these vision therapy for convergence insufficiency, we didn't have funding to do a big randomized controlled trial. So what we did was we said, well, what we're going to do is we're going to not tell our participants that the exercises are training their convergence, so they should improve their convergent fusional reserve, but not their divergent. And so when we found in this study that the people who had the vision therapy, their convergent fusional reserve improved, but their divergent didn't change, the task to the patient was very similar. So this was some indirect evidence that they worked. Not as good as a randomized controlled trial, but somewhat useful. Double dissociation. This is the best example of double dissociation. A very, very clever experimental design. This guy, Del Osso, is a famous nystagmus researcher, and he noticed, like other people, that contact lenses seem to help a little bit in nystagmus, not much. And he argued that it's the subconscious feedback of the eyelid and the lens when the lens moves. So what he did was he did a very nice experiment where he got people with nystagmus and he measured their eye movements, and he then fitted with contact lenses, and he showed the nystagmus seemed to get better. That could be a placebo effect, so he repeated the experiment using a topical anaesthetic eye drop. And the benefit from the contact lenses no longer happened. Now that's not as good as a randomized controlled trial, but it's double dissociation. It's a way of trying to control the placebo effect without a randomized controlled trial. So conclusions, we are subjective. That's why we love human beings. We're lovely and subjective, but it means that research needs to be objective and an evidence-based approach is essential. Martin Luther had this wonderful phrase, medicine makes people ill, mathematics makes them sad, and theology makes them sinful. What a skeptic was he, cynic even. I don't think he's right. I disagree with him in many ways, but we do need to be self-questioning. Not perhaps this cynical, but we need to question what we're told in science, and we need to question, particularly because we are trying to convince people that we are a profession to be taken seriously. And the way to do that is through an evidence-based approach, through being self-critical of what we do and not believing necessarily what we're taught. Thank you very much for your attention. I'll be happy to take any questions. The wonderful thing about Israel is questions come throughout the talk, so it's good because it's much better to come then. It's nice and lined up that way. Okay, so